Welcome, everybody. It's my pleasure today to introduce Siddharth Pritam, and he'll be telling us about swap, shift, and trim to edge collapse filtration.
Okay, thanks, Henry, for the introduction, and thanks the organizers for introducing, for letting me, speak at the seminar. So this is joint work with Mark Bliss from India. So basically the problem we want to solve here is efficient computation of persistence diagram. And as you might know, that persistence computation is still slow, especially in dimension greater than 1 and even greater than 4 is really slow. So the main problem, even despite the fact that we have cubic time complexity and in practice it works linear, the main bottleneck is the size of the complexes, which is exponential with dimension. So Rips complex, which is one of the most popular simplified complex used in TDA, topological data analysis for persistence computation, because it's easy to compute and it's a flat complex, meaning that it is characterized by underlying graph. So the simplicities of Rips complex is basically the cliques of the graph. So here you have triangles and tetrahedrons as the clique. So Rips complex is one of the most popular, simplified complex for persistence computation, and it approximates basically check filtration. So in this in Rips complex, the size grows really exponentially with the dimension as check complex. So for lower dimension, I think it's more advisable to use alpha complex rather than Rips complex. But beyond dimension 3, Rips complex is really only choice we have because we can compute it easily. Okay, so this is why it's important to focus on computation of persistence of flat complexes. So this is what the topic of this talk, and there has been a lot of work in past, and this is one of the central topic for research in TDA and in persistent homology computation in particular. So there are, like, as you might know, that computing persistent homology involves reduction of a boundary matrix. So the first approach by previous researchers is to come up with better improved reduction algorithms. So some of the technique which has been employed is, like, instead of computing homology, compute cohomology. And there are other optimizations such as like clearing optimization and chunk algorithms, so things like that. They have been employed to have an improved reduction algorithm. A complementary direction has been explored as well, where we try to pre-process the input filtration to a smaller filtration in an exact or an approximate way, and then compute the persistence of the reduced filtration. So one of the classic work in this direction is sparse Rips by Don Sheehy. And then there are techniques developed by Vidit Nanda and Michelle Cove using Morse theory. So, and there are a few other works in this directions as well. So these are very general kind of approach for general simplified complexes. There are Rips complex centric approach as well. And the most famous one is the Ripser. It's a software which is developed to compute persistence of Rips complex. And this is really amazingly fast software. It's hard to beat this one. And there are several other softwares which are based on this, Ripser++. So these are the basically softwares available for computation of persistence of flat complexes. Then recently we developed two techniques which is basically a pre-processing mechanism to reduce a flat filtration to a smaller filtration. So the first technique uses strong collapse. So this is a strong collapse was introduced by two Argentinian mathematicians, Bermak and Minian. And so here we basically remove a special type of vertices. And through this removal of special vertices, we basically get a smaller filtration and then compute the persistence of the smaller one. Then later on, we extended this technique, strong collapse, to edge collapse, where we remove special type of edges, and we show that experimentally that this method works better than the strong collapse. And in the current one, what we did is that we revisited this method, and then we basically deconstructed the whole algorithm and found out the underlying principles are much better, much simpler than what we presented. So once we get hold on to the underlying principles, it was easy to play with the algorithm and come up with new variants. And one of the variants we tried, which is basically processing the edges in backward directions rather than the forward direction, yielded much better results experimentally. So we will talk about basically this the backward algorithm here. So the setup is as following. So we have real numbers, which are like indexed by some natural numbers, and ti is less than ti plus 1. And so these are basically our filtration values or grades. And then for each filtration value, you have a graph associated with this. Okay. So these graphs are associated, linked through inclusion maps. So this is kind of filtered graph. And then associated to the filter graph, you have filtered flag filtration. So you basically compute the clique complex at each TI, and then you get a flag filtration. Okay. So essentially what you have is an ordered set of edges. Okay. They are ordered according to filtration values. So for each edge, you have two numbers associated. Its order in the filtration and its filtration value. Okay. So this is the setup, the input we have, and then so I'm basically assuming that we all know what persistence is, and so persistence will be a kind of black box for the whole talk. So the definition, I won't go into the details of the definition of persistence diagrams and things like that. So now, given that input setup, what algorithm does is that it basically performs three basic operations, which we call swap, shift, and trim. So these operations are performed over the edges of the filtration, and these operations manipulate these two numbers associated to each edge. And after this manipulation, we basically get a smaller, reduced, equivalent flag filtration. So the input is a filtered graph and the output is a filtered graph. So we basically try to minimize the whole, trouble of expanding the graph to the full simplified complex and then doing all the reduction. So the source of improvement here is that the whole algorithm works only at the level of graph, and it reduces the size of the graph. So basically the gain in terms of simplified complex is much more. So let me introduce the key notion which we use in the whole work. So this is the idea of dominated edge. So I mean, this can be defined for any simplex. So here we will basically focus on the edges. So an edge would be called dominated if its link is a simplicial cone. So you have apex V prime, and then there is subcomplex L. So in this example, we have two tetrahedrons glued along this triangle sigma O. Now, so if you look at the link of this edge sigma, you are basically the link is these two edges, which is a simplicial cone, and its apex is this vertex O. So sigma is dominated by O in this example. Now the key property of this dominated edge is that if I remove that edge, it corresponds to many simple collapses, elementary collapses, which means that it basically, the removal preserves the homotopy type. So in terms of homology, it translates like this. So the inclusion induced by the homomorphism induced by the inclusion, so removing sigma here, is an isomorphism. So this is the key property of the dominated edge, so which makes this edge basically useless in terms of persistence computation or topologically. The important factor is you can find domination of an edge very cheaply in flat complexes. So all you need to do is to look at the neighborhoods. So if the neighborhood of the edge is contained in the neighborhood of the vertex V prime, then E is dominated by V prime. So this is basically the source of improvement for the computation. So as long as you have an edge, which
Siddharth,
basically gives you this, it could be, and it does not have to be dominated edge. It could be any edge, as long as it gives you this property over homomorphisms on the homology level, the whole pipeline will work.
Siddharth, can I ask a question here?
Sure.
Yeah. So when you have this condition, the neighborhood of the edge is contained in the neighborhood of V prime. V prime is not allowed to be one of the vertices of the edge, right?
Yeah, sure. No. It has to be different than E. Otherwise, E will be always dominated.
Right.
Because it's defined as the
intersection
of two. Yeah.
Thanks.
Sorry, I should have defined the. Yeah.
No.
Yeah. Okay. So this is the two main points here about dominated edges. Okay. So now let me come to the operations. So the three operations we talked about. So first we look at shift. So what we do is that we shift an edge if it is dominated at the time of insertion. So let's look at this example. You have this graph, and if I look at this edge AB, at the time of insertion, you have just these three edges, and this edge is dominated by the vertex T. Okay. So it actually does not contribute to the topology or like persistence diagram. Like the moment you include this edge, the triangle also comes into the clique complex, right? So I mean, this deformation retracts to these pair of two edges, and essentially, I mean, it does not contribute anything to the persistence diagram, right? The pair 3, it is paired with a triangle, and basically 3 is a diagonal element in the persistence diagram. So instead of 3, if I write 2.9 or 3.1, it does not matter. Like I could, change the filtration value, and I will still get the same persistence diagram. So this is the intuition. So what we do is that we shift it to next available filtration value. Instead of like choosing anything arbitrary, we go to the next filtration in the graph. So this is what shifting is. So I change the filtration value from 3 to 4 here. So in the pair of values associated to the edge AB was changed from 3.3 to 3.4. The red one is the filtration value, and the green is the order in the. Okay, so this is shifting. Okay, and we proved that this basically preserves the persistence. This operation would not change the persistence of this graph.
Can you say again what the green and the Siddharth? Can you say again what the green and the red are?
So the green is the order, it's like the indexing of the edges, and red is the filtration value.
I see. So green is sort of a total order where every simplex has a different value.
Exactly.
Okay. Yeah. Thanks.
Exactly. Yeah. Okay. So now let's look at the second operation, swapping. So it's a bit more trivial. So if I have two edges and they have the same filtration value, for example, AB and BH. Okay, they come at filtration value 1. So, I mean, I can choose the total order arbitrarily. Basically, I can assign this 5 and assign this 4, and then the persistence would not change. So this is what swapping is. Sorry, yeah. So here, I mean, the green value has been changed. They have been swapped. Okay, so they have the same filtration value. So I can choose 4 here or 5 here, or I can assign 5 here or 4 here. So clearly this would not change the persistence diagram. So this is swapping. And then the last one is trim, which is essentially a special case of shifting. So if the dominated edge is the last one, the very last one in the filtration, then there is, I mean, I can choose the next filtration value as infinity, basically. I can shift it to infinity, which is essentially trimming, removing it. So you assign, I mean, change these two values to infinity. So the order, I mean, basically I trim it out, remove this edge. So these are the 3 basic operations we perform over the edges. Here we chose domination as criteria, but I mean, I could choose anything as long as it satisfies those two conditions. I mean, just only one condition over the homomorphism, in fact. But for computation purpose, it has to be cheaper. Like if it's for the whole thing to work on the graph, I should have something over the neighborhood. The criteria should involve neighborhoods. Okay. Any questions until here? All right. So these are the three operations we have. Now the algorithm is basically using these three operations. So we move backward in the direction. So you have the total order over the edge, and we start from the very last edge, and we see what we can do with that edge. And once we are done with one edge, we never touch it again. So we basically pick one edge, and then we perform these three basic operations over it, and then we keep moving towards the beginning. So in this example, this edge AC is the very last edge, has filtration value 4 and it's ordered 5th. And this is dominated here by B. So I can just remove it. I trim it basically. I perform trimming and I get this graph as a result. And of course, this has the same persistence as this one. Now the next edge to consider is CB, and it is non-dominated. There is no edge to dominate it. So I would not do anything. I wouldn't touch it anymore, and I'll leave it as it is and move to the next available edge, which is AB. Okay, AB is dominated by D. So now I can't trim it because there's something after it. So I will shift it until the next filtration value. So I shift it, and so I make basically the shifting involves changing the filtration value to 4, the next available one. Okay, so now this one has the same filtration values, right? 4 and 4. So I can swap their order. So I swap it, it became 4, and this became 3. So now this is the very last edge. So I can trim it. So I trimmed it. And now this is the very last, the 3 edges, which is the minimal required number of edges to make this a connected component. So, I mean, the algorithm will go after this, but this is basically the output of the algorithm. And there are several other optimizations which is very crucial for the speed up. So the thing is that, for shifting, I don't need to always shift to the next available grade. I could actually shift to the next available grade in the neighborhood of the edge, because the domination is only affected by the neighborhood edges. So if the neighborhood edge, the next available grade in the neighborhood is beyond 4, or it's 10, then I could shift to 10. I can skip all the intermediate filtration values. So these simple optimizations are very important in the algorithm. So, and the runtime of the algorithm is linear in terms of input size, number of edges, and cubic in the maximum degree of the input graph. So this is pretty fast. So we perform certain experiments to show to understand how it behaves in practice. So one of the interesting experiments we performed was over Torus. So it's a 2-dimensional manifold embedded in R3. So this is the filtration value of the edges, so the length of the edges, and these are the total number of edges. So orange one is the original, input graph. So as you see, there are like 0.8 million, more than 0.8 million edges here. And after performing our algorithm, so this backward algorithm, this is the output graph. So you see that from 2.6, the filtration value dropped almost to 1.4. And in total number of edges are also very quite minimal. So other interesting point is that this curve has a very interesting pattern, like this almost like step function. So we can zoom it and try to understand, and it actually gives us certain topological insight, like what is going on here. So from this filtration value to this filtration value, there is no extra edges in the core, in the output graph. So the edges, what happened here is that the torus is formed at this filtration value, and now whatever we include, they are basically dominated. So they are being removed. So that there are 2 cycles and one 2-dimensional hole here. Okay, but there's sudden jump from here to here at this filtration value, because the topology has changed. So the inner loop, the cavity is being basically filled up, and we have just one circle left. Okay, and this continues until they here. So now the next edges which are appearing are basically dominated, so they are being trimmed out. And from this, at this point, there is a little bit jump, because at this point the whole complex has become cone. It's contractible. So now we include certain edges, but after that everything is cone. So the longer edges are dominated, so we can just throw them out. So this is really interesting experiment to show what actually happens in from the topological perspective, what's going on. So the original motivation of the whole process was to speed up the computation of persistence diagram. So we compare ourselves with the previous forward algorithm, which we had 2 years ago. So so we can see that there is a factor of 10, like we achieve almost factor of 10 in time. So there are two variants in the backward. There's dense version and there's sparse version. So dense for the dense graph and for the sparse graph. So the reduction size is almost same in both algorithms. But in some examples, for example, in this complete graph over 900 points, we see that the backward algorithm performs much better than the forward one, and in terms of number of output size. So these are the first run of the backward algorithm. So you can actually run these algorithms multiple times. So you can run over the output of the previous run. So you can keep running until it converges. So yeah, I mean, these experiments show that the new algorithm is of course faster. The next thing is that you can parallelize the algorithm. So these three operations which I described, shift, swap, and trim, they are very local in nature. So we can perform several of them in parallel. So basically, this is, I mean, using this idea, we try simple, divide and conquer strategy. So given this set of ordered edges, we split them into two halves, and we process these two halves independently. So you have, this is the left half and this is the right half. After processing this, we selected certain edges, the green ones, and we discarded the red ones. So these are the trimmed out. Similarly, for the right, you have these edges. Okay, so this edge, so now to join the solution, this edge is a set of edges are really discarded because there is nothing after it. So it does not have to shift through them, but these set of edges must be shifted through the next these edges, because they, even in the previous order, they were after these edges. Right? These red ones were kind of before the green ones. So to join these two solutions, basically we try to shift this set of edges across these ones, and whichever has passed through, we discard them, so trim them out, and the edges which couldn't pass through this set of edges are kept in the total solution. So I mean, of course, we can do this, not just one split, we can do it multiple splits. So this is the basically idea behind the parallelization of the code. So we did implement a basic prototype of the parallel version, which assumes that the edges have different filtration value. They don't have the same filtration value. So this is the total number of thread, and this is speed gain. And so this is 8-core computer CPU. So in some examples, I mean, the gain is quite good. It's a factor of 5 and 3, which is not bad. But in these couple of examples, we see that there is not much gain with respect to parallelization. So it really depends on the data set. So this is still in a child phase, this implementation, but it has some potentials. And it also depends where we split the sequences. So these factors are crucial in the parallel version. Then another extension is that you can, by simple tweak, you can have an approximate version of the algorithm. So I mean, the idea is that if an edge is non-dominated for small interval, for example, epsilon, and it is dominated afterward throughout the filtration, then it's tempting to just remove them. Right? We don't need, like, it can incur just a cost, like error of epsilon. But the problem is that these errors could piled up and can be like it might not be controlled. So we basically did a little bit slightly simpler thing. So what we did is that, so like I explained, if an edge is included at this time, we try to test its domination epsilon later around this point. And if it is dominated throughout, we remove it. But if it is non-dominated, we find it being non-dominated at this filtration value, then we keep it back to its original one. So this way we control the error. Okay. So we implemented this version. So there are two motivations behind approximate version of the code. First is to have a bit more smaller output if it at the cost of some error, and second is the computation time. But we find that in many examples, I mean, there is not much gain. Exact version performs as good as the approximate one. But there's one example of circle, which is quite a natural example, that approximation does have impact. So, and very small approximation, like 0.1. So this is multiplicative. What I explained is additive here, but you can use any function. It does not matter. You can do anything here to create the gap, and this will work. So like a small multiplicative error gives us quite good result in terms of circle. So this was about the standard persistence diagram. Now, I mean, this, so let's try something a bit more complicated. So we tried that, and so we tried for zigzag persistence. So zigzag persistence, as most of you know, that it's basically, it's like standard filtration, but the complexes could be linked through inclusion and removal. So this is filtered graph. Zigzag filtered graph, and you can have associated zigzag filtered flag complex, or in general zigzag filtrations. So you can basically include edges and remove edges. So the main question while trying to do these things for zigzag persistence is that, can we shift through edge removals? So for example, here we have this edge F, which we include here, and it is dominated. Can I shift it through the removal of edge E? So what essentially in this example it means is that, can I swap these two operations? So I remove E first and include F later after that. And if you look at this example, in the top sequence, there's only one dimensional persistence whole. Basically, it persists through the whole sequence. And in the below example, you have, it splits into two. So you have one bar from here to here, another bar from here to here. So clearly, we can't do it in general. But what we showed is that if the F is dominated after the removal, then you can remove it. So it has to be dominated before the removal and after the removal. Then you can basically shift this edge. You can swap these operations. So this was the, like, in terms of the operations, the three basic operations. This was the main bottleneck, which we saw that in special cases you can, which is not so uncommon in practice, you can do that, where it is dominated after the edge removal. There are other like things which is involved in zigzag, is that the goals of simplifications. So in the standard, the usual persistence, the goal was simple. You start with the edge, you try to shift it until the end and trim it out. That usual is, it could be applied here too. So if an edge is dominated when it was inserted and it was never removed in the sequence, then you can shift it towards the end and trim it. The other thing which could also be done is that if you include the edge and and remove it, and at both instances it's dominated, then what you can try to do is that, see if we can shift the inclusion towards the removal, and then once it arrives there, dominated, can I so basically then we can unhighlight it. We can cancel both operations together. So this way we remove two operations at once, and this is very common in practice. Like it happens, some edge is included and removed immediately. There are examples for in practice, there is way to compute standard persistence using zigzag persistence, where this is very common, this phenomenon. And and the other thing about zigzag is that it's symmetric. So, I mean, it's inclusion removals, and if I move this way from left to right to left, is the same thing. I mean, what I mean is that basically here, for example, in cancellation approach goal, I try to shift the inclusion towards the right to basically make it closer to removal, its own removal. Symmetrically, what we can do is that we can try to shift the removal towards the inclusion, because if I see the removal from the other end, it's inclusion. So this is a symmetric, in a way, it's a symmetric sequence. So I can apply, this algorithm into both ways, from the both ends. So the whole process becomes a bit more delicate in zigzag simplification. We haven't implemented the zigzag version, but it would be interesting to see how it performs, because computing zigzag persistence in general is harder than usual standard persistence, and it would be much more useful to have a smaller input to compute the zigzag persistence. So, but we don't have the implementation of the algorithm yet. So the future work is, can we use these things, reductions, to have a homeomorphic constructions, basically a triangulation? Can we, compute triangulation from Rips complex? So collapsing a Rips complex to a triangulation, which is homeomorphic in a way to underlying space from which the data is picked up. Another extension is into multi-parameter persistence, and it has actually appeared in YRF at this year's sausage. So yeah, with this, I thank you very much for your attention, and if you have any question, please ask. So.
Wonderful. So before we get to questions, let's first briefly unmute ourselves and applaud for the speaker.
Thank you.
All right, so let me start with either a question or a comment from the chat. And David, please unmute yourself. At some point, if it'd be possible to make a pictorial representation, of the example on the torus. David, do you want to say more?
Yeah. Hello.
Hey, go ahead.
Yeah, I have. I wanted to find out if in your experiments you actually triangulate the torus, or you just look at the torus in the two-dimensional frame, or you have to triangulate it into a complex before performing the experiment on it. That's why I wanted you to do a pictorial presentation of how you actually underwent your experiments.
So your voice was a bit cracking, so I couldn't understand the second part of your question. So could you please repeat?
Okay, so I was much concerned with the experiment that, are you looking at the torus in a two-dimensional, like you take the two-dimensional torus, or are you rather triangulating the torus into a complex, then performing experiments on it?
No, so yeah, so the setup was that you have this, we sample points out of a torus, so we don't get the torus as such. So we have the function describing the torus, so, and then kind of the closed form solution, and then from that we picked 1300 points, something like that, and then we started connecting edges if the points were this far, that far, so through that, and then you got the graph, and then at the top of the graph you compute the clique complex over it, and then you compute the persistence. So we didn't triangulate it, just to give you. So we basically got, so the experiment was run over the point cloud. So we got the point cloud which was sampled out of a torus, which is embedded in 3D.
And then the Rips complex sort of fills in triangles and tetrahedra for there. So I wanted to ask, while you're on the slide, I wanted to ask a question. So, okay, so you first obtain the torus homotopy type and you can collapse down. And then next you would obtain the homotopy type of the circle, right? A solid torus. So conceivably, that one could collapse down further, right? You know, for a torus, you sort of need a quadratic number of edges. For a circle, you just need like a linear number of edges. So do you have any intuition for why it doesn't collapse further? You know, or
it's like, you know, the edges kind of forms. So imagine like you have a square, let's say, and to fill the square, you have one diagonal, right?
Yep.
So you put that diagonal. Now they are filled. So if you add one more diagonal, you can remove it, right? The extra diagonal is additional, you don't need it. But the central one, you need one, right, to keep it. And now this is homotopy to a point. So by edges you can't further reduce, but if you start removing vertices, you can get to the, but you know, this way. So the intuition is like that. So I mean, you can remove in 1D, you can do that, right? The corner edges are still dominated, but in 2D it gets a bit more complicated, right? Sorry, in 3D loop, you see the boundary is also two-dimensional thing. So the edges on the boundary. So now imagine this circle, right? This, and I don't know how to say. You had this square, right? Now the torus is basically joining these two edges together.
Right.
So glue them together. So now you can't see.
There's no free edges. Yeah.
Free edges, yeah.
So have you considered trying to incorporate the removal of dominated vertices into algorithms like this as well?
Yeah. So the first one was using the removal of the vertices, the strong collapse approach, which we mentioned. I mentioned in the beginning of the talk. So you can do that, but I mean, interestingly, that is more costlier than this. I mean, you can plug and play. So you have these two solutions. You can try doing one first and then apply the second, and then you can, you know, play with these two approaches. But I think I mean, because later on you have to add the edges again, so it might be that you'll expand it back. That if you. So what happens in the strong, if you remove the edges, vertices, the problem is that you don't get inclusions. You get simply cell maps.
I see.
So you get a tower. So you have to expand it back to a filtration. So when you expand it back, you will get a lot of things.
I see. So you can combine the two ideas, dominated edges and dominated vertices, but they don't play together as so nicely all the time.
Yeah.
In this algorithm where you're looking at the dominated edges, do you need to assume that all of the vertices appear at time 0, as happens in a Rips complex, or no?
No. It can happen.
The other question, I'm just
sure.
shooting out all of my questions. Is there some play people can go to sort of try out the code?
Yeah. It's actually published in Goody. Sorry, I forgot to mention that. I should have mentioned. It is available in Goody as an official, like in the official version of Goody. So, yeah, you can play with it. And if you have any more ideas, please let us know.
Okay.
So this version is actually in Goody, and we also have at least one GitHub repository. So I'm sure this is an official version now. So.
And let's say somebody wanted to compute a Rips complex just at a fixed scale, you know, a single scale. You know, would you suggest this algorithm or ideas along these lines? Or do you really think of the problem of, you know, computing, you know, the homology groups of the Rips complex at a fixed scale as a quite different problem?
No, I think we can try these ideas. Like, it's not about. Essentially, dominated edge is basically preserves the homotopy type. So at the fixed scale, you can apply the same. So imagine that you have the say one filtration value, right? But you can still have the total order, and you can play with these things. So eventually, the persistent homology at one scale is the homology, and the whole idea will go through.
Okay. Yeah, there's a computational challenge that I'd be interested in if anyone can do, which is, if you sample points from a circle and you build the Rips complex, you can sample enough points so that you see the circle and then the 3 sphere that comes up and maybe even the 5 sphere that comes up. So you can see that in homology. You can, from a dense enough sample, once you reach the scale, you can get the 3-dimensional homology. But the example that I haven't seen computed is take the 2 sphere, okay? And then once you reach the scale of the tetrahedron, we know what the next space is. It's this 2-sphere join SO3 mod A4. And its homology groups are known. So its 4-dimensional homology is Z mod 3Z, and its 6-dimensional homology is Z, and it has no other homology. But from a dense enough sample of the 2-sphere, right, and then take the scale parameter slightly bigger than this, you would imagine that one should be able to compute those homology groups, but I have no idea whether that's within reach anywhere in the near future or not, or if that's sort of like, we still need some more years.
So from the computational perspective, you're saying like it's hard to compute because the samples are really dense, so you have a lot of simplices, and then
yeah, you'll need the sample to be dense enough so that one tetrahedron is connected, to nearby tetrahedra through 4-dimensional simplices, right? So it'll have to be dense enough to allow that. Just sort of like in the circle, to get the 3 sphere that comes up, the H3 that appears, you need the sample dense enough so that your nearly equilateral triangles, are connected through higher dimensional simplices to the adjacent ones.
I see. Yeah, these approaches could help in simplifying, but I don't know how much. It's worth trying because it can be interesting to see. Especially, I think vertex collapse would be more useful in this thing, because you can reduce, like if you remove one vertex, you really remove a lot of simplices around it. So as you increase the dimension of the simplices, the star gets a bit smaller, like right around the vertex there are a lot of simplices. So if you remove a vertex, you remove really a lot of simplices. An edge a bit more, less than the vertex, but still quite a few. So if you keep on increasing, for example, the highest dimensions maximum simplex has no star, it's the star of its own. So the vertex collapse would be interesting to try.
Yeah, if any folks are interested, I'd like to know what you find. More questions? All right. Well, if not, let me thank Siddharth again for a fantastic talk, and I'll stop the recording here.
Thanks. Thank you very much.